So you might be wondering, if I'm not going to use a bar graph for continuous data, what type of graph should I be using instead? So let's talk about this. The type of graph that you should use depends on the sample size of your data set and also a little bit on the data distribution. So we'll start off by thinking about very small data sets. If you are working with a small or very small data set, then you are going to want to use a dot plot. Dot plots can also be used with medium sample sizes depending on your preferences. You can use a dot plot with any data distribution or if the sample size is too small to determine the data distribution. And a dot plot simply shows the value of every individual data point in the data set as a point. One of the things that you need to be careful of when you're making dot plots is to check the software that you're working with carefully to make sure that it's making a dot plot and not a histogram with dots. So what is a histogram with dots and why should I avoid this type of figure? Well, when we have a dot plot, we have the figure here shown on the left, which shows the measured value of each of our individual data points. What some softwares will do is they will actually create a histogram by grouping the data into bins and then moving each point to the center of the bin. And so here's what this might look like if we have 20 bins, 10 bins, or 5 bins. And you can see that we end up with a very regular spacing of intervals between the data points because those points are being moved to the center of the bin. So the fewer bins you have, the more dislocation. This is called a histogram with dots. So what you want to do is take whatever software you're using, enter some data that are irregularly spaced, and look at the graph you get back and see if they come back as being regularly spaced and if the points have been moved. If they have, then your software is making a histogram with dots, and you want to find something else that's going to make an actual dot plot and not change the values. Okay, the next type of figure that you can use as your sample size starts to get a little bit larger is a dot plot combined with a box plot or a violin plot. So dot plots are best for very small data sets because the summary statistics that they show are shown in the larger graphs are only meaningful when you have enough data to summarize. As we get larger data sets, then the summary statistics shown in box plots or violin plots become more meaningful, and therefore it makes sense to combine those with the dot plot. So here you can use these for medium sample sizes and again with any data distribution because the data points themselves will be visible. The next options for the type of figure that you might use as your sample size becomes larger are just the box plot and violin plot alone. At some point, you will end up with too many dots to really see. They'll start to overlap over each other and it'll be a big mess. And at that point, you have enough data points that you can have a box plot or a violin plot. Now, a violin plot you can use with any data distribution. However, box plots should be avoided if you have bimodal data. And the reason for this is that the two bimodal peaks will be hidden somewhere in your dot plot and they won't be visible. Whereas if you have a violin plot, then those two peaks will be outlined and you will clearly see them with an hourglass shape on your violin plot. And lastly, let's talk about the bar graphs. Bar graphs are best used for counts or proportions, these are both variables where the bar height shows the value of the count or proportion. You can use them with any sample size and with any data distribution. However, bar graphs should not be used for continuous data. Okay, so you might be thinking, I still prefer bar graphs because they convey a clear message. Sometimes it's hard to see what's going on with dot plots. The important point here is that often we don't have to make a choice between having a clear and informative data visualization and showing the information that readers need to critically evaluate the data. We can do both. So let's talk about how to do this. There are two steps. The first step is we want to make sure that all of our data points are visible. So sometimes when investigators first start making dot plots, they'll do what's called a strip plot, which means they put all of the data points in one single row on top of each other. And this is an issue because we can tell there are overlapping points, but we can't really tell how many points there are in some of these regions. So one option is to decrease the point size a little bit, and that really isn't particularly helpful with this data set. The next thing we can do is make the points semi-transparent. So now regions with more dots show up darker than regions with fewer dots. And this helps a little bit, but it doesn't really solve our problem. The next thing we can do is random jittering. So we add some random noise on the y-axis here, which is our group variable. It's not a measured value. And this spreads out the points a little bit so that we can start to see what's going on in those regions with more overlap and how many points there are. However, because the overlap is, or the jittering is random, we can still end up with overlapping points. So the best option is really to go with symmetric jittering. And with symmetric jittering, we align the points on either side of an imaginary line through the center of that group so that we can clearly outline the shape of the data distribution with our eyes. So first step, make all of your data points visible with symmetric jittering. The second step is we're going to use emphasis and de-emphasis to emphasize the summary statistic. So let's go through this step by step again. So we start off with our ineffective graphic. One thing that we can do to help here is increase the width so there's more white space between the groups and it's easier for our eye to separate them. And then we can emphasize the summary statistics. So we do those by placing them in black or perhaps in a color in red in the foreground. And then we put our data points in light gray in the background. And this means that when I look at the figure as a reader, my eye will immediately go to the feature that's emphasized, which is the mean or median line. But I can still take a second look at the figure to take in the dot plots, which will give me a sense of the sample size, the data distribution, the amount of overlap between groups, and that other information that I need to critically evaluate the figure. So make all your points visible with symmetric jittering, and then use emphasis and de-emphasis to emphasize your summary statistics. You might be wondering, can I just add dot plots to my bar graph? This is a common thing that people are doing now, and it's not one that I would encourage. So if the choice is between a bar graph without dots and a bar graph with dots, I would take the bar graph with data points or dots every time. However, dot plots are always going to be better than bar graphs with dot plots, and there are several reasons why. The first is that we very often shade our bars, and when we do that, we obscure the data points inside the bar. We make them less visible. The second is that the bars themselves and the vertical lines at the edges of the bar are actually chart junk. That solid shape of the bar creates the illusion of certainty without adding any information. So that bar looks just as solid whether I have 2 data points or 2,000 data points. And in reality, those are very different situations. I should be much more confident in the summary statistics when I have 2,000 data points than I should be when I have 2 data points. The third, if you have a zone of irrelevance in your data set, then this falsely alters our perception of the size of the difference between groups or the amount of overlap between groups. And again, this doesn't apply to every variable. Not every variable will have a zone of irrelevance. The last thing is something called within the bar bias, and this is where we incorrectly believe that points are more likely to fall within the bar than above the bar. So if readers are asked to estimate the likelihood of 2 data points that are equidistant, but one is above the bar and one is below the bar, people will rate the point inside the bar as being more likely. And there's other evidence out there that about 1 in 5 readers tend to assume that the data points fall within the bar and not above them. So the bar graphs can simply be misleading. In contrast, when we look at the dot plot, it contains all the information we need and nothing we don't. So we can easily see the magnitude of the difference and the overlap between groups, and the features that affect our interpretation of the graph, like the points, the summary statistics, the sample size, and the amount of overlap between groups are clearly visible. Okay, when is it appropriate to show summary statistics like error bars or box and violin plots? Summary statistics are really only meaningful when you have enough data to summarize. And here we have simulated data sets. And so in the first case, we have drawn 100 random samples with a sample size of 5 observations per sample. And then we lined those samples up according to the mean and standard deviation and plotted them on this graph. And then the second group in blue, we've done the same thing, only with a larger sample size, 20 per sample. So the true value of the population mean and standard deviation is shown by this black line is the mean, and then this gray region is the standard deviation. So if our estimates for each of these individual samples were reflecting the true values for the population, then all of these red and blue values would essentially fill the gray space. They would align with this black line and this gray region. But we see that that's not actually what happens. And with small sample sizes like the N of 5, the means and standard deviations can be very different from our true population values. So maybe I've only done one experiment. Maybe I got this sample here in the middle that is a mean that's very close to the true population value, but really underestimates the standard deviation by quite a bit. Or maybe I got this sample way out here on the right edge where the mean is much higher than expected and the standard deviation is also. In contrast, when we have a larger sample size, the summary statistics are much closer to the true population values, so we can have a little bit more confidence in the values that we're reporting. And so this is why the summary statistics may not be so meaningful or valuable when you have a very small data set and you might just want to show the dot plot with the mean or median line. Okay, why shouldn't I use box plots for bimodal data? We talked about this already, but essentially the boxes conceal the two peaks, and so we want to use a dot plot if we have a small sample with a bimodal distribution or a violin plot with a large sample, so that that bimodal distribution is clearly visible. How do I make effective dot plots or combined with box plots or violin plots? So here's a few examples. And so we typically combine a dot plot with a box plot or violin plot when we have a medium or small sample size. Here's a couple of examples of how that might look. So one thing investigators might do is simply show the box plot, and this is a little bit of a problem because, again, it's a small sample size. We're not so confident in the summary statistics. We're not seeing the data points. So in the second case, we've added a strip plot on top of that box plot. And here we know we have problems because we can't see the overlapping points, and it's a little bit hard to determine what that data distribution actually looks like. So what do we do that's better? So the first thing is we want to follow the same practices we would when we're making a dot plot and make sure all of our data points are visible, and we're going to use symmetric jittering to do that. In this case, we have some differences in sample size, so we've also made the width of the box proportional to the sample size so that those differences in sample size are visible to us, both in the width of the box plot and also in the dot plot. Additionally, we've added the sample size on the axis label below each group. No one wants to count your data points. They're busy, they have other stuff to do. And so clearly putting this information on the axis labels allows them to get that information without having to count your data points. And then lastly, we have this very small group at the end, which only has 4 observations and is far too small for a box plot. And so we have removed the box plot for that group and only shown the dots. Now, there are 2 ways to do this. We can either emphasize the dot plots by putting them in black in the foreground and de-emphasize the box plot by putting it in gray in the background, or we can do the reverse. We can emphasize the box plot by putting it in black in the foreground and de-emphasize the dot plot by putting it in gray in the background. For the sample sizes shown in this figure, I would emphasize the dot plots. We want to emphasize what's known. These are very small samples, so the box plots are a little uncertain. So I would emphasize the box plots for this sample, or the dot plots for this sample. Whereas if I had a larger sample, then I might want to emphasize the box plots. And I've shown this example here using dot plots combined with box plots, but you can also use exactly the same strategy if you are combining a dot plot with a violin plot. Okay, so when I showed this figure that you saw earlier in the presentation, I sometimes get questions about, doesn't the y-axis always need to start at 0? Let's talk about this because this is a really important point. This idea about the y-axis starting at 0 is an illustration of what can happen when we take a particular visualization that was designed for a certain type of data and we use it for a completely different type of data, and we try to transfer over all of the rules or guidelines that come along with responsible use of that visualization without thinking critically about what's going on. And so we have to remember here, bar graphs are designed for counts or proportions. And so this is something like 25% of people had salad for lunch. 50% of people in my sample had hypertension. So here we're just looking at a counter proportion. 0 is the true minimum value, and so it makes a lot of sense to start our axis with 0. The bar height is meaningful. We can think of the bar as being filled with data. So the higher the bar is, the higher the counter proportion. And so this is what bar graphs are designed for, and this is why the guideline about starting your axis at 0 makes sense for those types of graphs. So 0 is our true minimum value. Higher the bar, the higher the counter proportion. And so this axis is giving me visual information about what that proportion is. I look at it and I see 90%. When I cut the axis, I alter my perception of the counter proportion. So here, the bar graph starts at 80%. So the proportion that I see is 50% instead of 90%. And this is where the issue comes in. Now, let's talk about what happens when we're graphing continuous data. In continuous data, the bar height is arbitrary because 0 may not be the minimum value, and in many cases, 0 might not be a biologically possible, physiologically meaningful, etc. Okay, so with continuous data, we know our bar height is arbitrary, 0 might not be the minimum value, and our graph goal is different. We really want to show the data distribution and the amount of overlap between groups. So we can have a variety of different scenarios that we can see here. In the first scenario, I have negative values, so there are values that are below 0 in my data set, and I don't think there's anyone that would argue that we should start our graph and axis at 0 and just pretend that these data points don't exist. That would obviously be inappropriate, and so we clearly have no problem changing the axis value here. The next scenario we might have is a very large zone of irrelevance. And so maybe our data points are really clustered in the top quarter of our graph. And when we start our graph at 0, what happens is it becomes very difficult to see the data distribution, the number of data points, those pieces of information that we really want for continuous data. And so in this case, a cut axis would be quite helpful to give us more information about the data distribution, the overlap between groups, the sample size, those things we really need to know. In the next scenario, we have a small zone of irrelevance. So here, starting the graph at 0 is not a problem. It doesn't really interfere. We can still see the sample size. We can see the data distribution, the spread of those data points. So 0 as a starting value is perfectly fine. Small zone of irrelevance, no issues here. 0 makes sense as a starting value. So what should you do with all this? The recommendations are to choose a scale that makes sense for the data set that you're working with. So if you need a negative starting value, start with a negative value. If you have a large zone of irrelevance, you might want to start your graph a little bit higher up so that those data points will be visible. If 0 makes sense and your zone of irrelevance is small, start at 0, that's fine. If you are using an axis cut, then you can emphasize that by using either a double line that goes all the way across to draw people's attention to this axis cut, or a wavy line that runs the entire width of the graph. And again, a double line to illustrate that there was an axis cut here and we're not seeing the values starting from 0. Okay, so you might be wondering, do I need expensive software to make these figures? And the answer is no. There are lots of free online tools and resources available that you can use to help make better graphics, including the ones I've discussed in this presentation so far. And so if you see table 3 in the circulation paper that I mentioned earlier, you'll find a list of different options of visualization tools that you might want to use to help you visualize your data. And if you are an R user, we also have an R flipbook, which shows you line by line how to make all of the graphs that are shown in this video. And you can access that on the Open Science Framework. Does it matter how I did my statistical analysis? Again, I'm so glad you asked because it definitely does. Again, the figure structure tells the reader about the experimental design and whether it matches with the analysis. So we want to avoid sending mixed messages. We want to make sure that that figure structure is providing accurate information about how the study was designed and how it was set up in the experimental structure. Let's take a look at a common example of how we see this done incorrectly or improperly. So let's say our experimental goal is to compare two kinds of mice. We'll call them a wild type and a knockout mouse. And we measured 3 different biomarkers, A, B, and C, and our goal was really to compare these wild type versus knockout mouse, not to compare the biomarkers to each other. And so for our statistical analysis, t-tests were used to compare the value for each biomarker between the wild type and knockout mice. What people will often do is put all 3 of those biomarkers on the same graph. And this creates a problem because as a reader, when these things are on the same graph, I expect that the goal was not only to compare the wild type and the knockout mice, but also to compare the biomarkers for each other. And so then I'm confused about why only the wild type and knockout mice were compared and there's no comparison of the different biomarkers because the figure structure is telling me that the biomarkers should be compared as well. So how do we fix this particular example? We want a figure structure that matches the study design and shows that the authors did not intend to compare biomarkers. And so here I have a separate panel for each of the different biomarkers. And then it's obvious to the reader that I only intended to compare the wild type and the knockout mice, and I did not intend to compare the biomarkers to each other. Okay, so how do I design figures that match my study design and statistical analyses? Well, for simple analyses of small data sets, it's often best to show one graph per analysis, and the graphs should include all groups or conditions from the analysis in the way that they were handled in that analysis. Let's take a look at some examples. So let's say my goal is to compare groups, and we'll build on the example we were just using of the wild type and the knockout mice. And so I would have one figure showing all groups as they were included in the analysis, which in this case is just my wild type versus knockout mice. Now we have the scenario from the previous slide where I have several different dependent variables or outcome measures, and here biomarkers A, B, and C. And so here, our goal is to compare the wild type and knockout mice, not to compare the biomarkers to each other. And therefore, I'm going to have a separate panel for each of the biomarkers so that it's clear that those things, the biomarkers, were not to be compared to each other. What if I'm comparing groups with pooled subgroups? So let's say I have male and female mice, but I pooled them for the analysis. So males and females were analyzed together. So here I can use different colored dots or filled dots versus open dots to show that I have 2 different subgroups. And this also allows readers to see that those subgroups were pooled. So those 2 subgroups are present within the same main group, either wild type or knockout. And I can look with my eyes and see, oh, it looks like the males and females do have similar values. I don't see any obvious differences between the 2. So it looks like it makes sense to pool those 2 subgroups. What if I do a stratified analysis? So maybe I have male and female mice and I analyze them separately. One analysis for female mice, one analysis for male mice. So here I have 2 separate analyses. So I want 2 graphs, one for the female mice and then a second one for the analysis of my male mice. And then maybe I'm testing for an interaction. So I have male and female, wild type, and knockout mice, and I want to see whether there are differences across these 4 groups. So in this case, I have 4 groups that are all part of the same statistical analysis and all analyzed separately: female wild type and knockout, and male wild type and male knockout. So these are all going to go on the same figure, one panel. so that it's clear that all of these 4 groups were treated as separate groups in my analysis. Okay, this is just a reminder. To confirm that your analysis is appropriate for the study design and the structure of your data, the reader needs to know exactly what analysis you performed. I won't go into detail on this today, but I will refer you to this paper. Very often in the biomedical sciences and in small sample size studies, the stat section might read, data were analyzed by t-tests or ANOVA as appropriate and statistical significance was set at p less than 0.05. And these statistical analysis sections are a problem because there are lots of different types of t-tests or ANOVA, and those tests may be appropriate or inappropriate depending on what your study design is. And so we really need to know exactly what kind of t-test or ANOVA you used in order to know whether that fits with your study design. So this paper provides a lot more detail and recommendations about how to report exactly which test you used, as well as your results in the figure or table legend, as well as in your statistical analysis section. Okay, so there are 2 exercises that we would encourage you to do after this module. If you happen to be writing a paper right now or will be soon, then we would encourage you to examine graphs that compare continuous data among your groups and think about how can you improve your figures using the principle discussed in this video today. If you're not working on a paper right now or you don't have any data that you can graph, then we would encourage you to critique a preprint or paper. It could be a past paper from your research group or maybe just another article in your field that you're reading. If you find a paper that inappropriately uses bar graphs, what would you use instead of bar graphs and why? And if the authors are using more informative graph types, then how would you suggest that they improve their visualizations? Thank you very much for joining this video today, and I hope you found this information helpful.